this application. Yeah.
This is on a uniprocessor?
Yeah.
Okay.
Yeah. It's running on one. I mean, it's running on one processor in this case. Right. So we ran now the application. So we knew where the data structure allocated. We only needed to look at the innermost loop. We went into all those malloc allocations that happened inside that loop and mapped them to large pages. So a lot of these large data structures are now on a large page. And we had a dramatic difference here. And so page faults went down. This is what we intended to have happen, and that certainly happened. And execution time went down by 40%. That was a huge effect. And it's due to the page faults. Page faults are very expensive high latency events. So by just looking at the page faults, we would actually think that's great, we are done. This was a very easy case. We are finished. But then we looked at the other data and the effects of this page fault, this page transformation on other performance data. And there we actually saw, well, TLB misses went down. That's certainly what we expected. We have much fewer page accesses now that we move to actually 60 megabyte pages from 4K pages. But there were some interesting side effects. And if you look here at the ERAT and as well as the L1 cache misses, we suddenly have this high band of misses here. That was a little strange that we didn't have there before. So we didn't recompile the application. All we did is we went into malloc. So we didn't change any of the data accesses. So the only reason for these additional cache misses are conflicts that we introduced. And then we thought about it by looking at this. Well, we now mapped all these large data structures aligned at the beginning of a large page. And if the application walks through the data structures, sort of each element in each iteration simultaneously, now we have a lot of conflicts. Before they were sort of lined up, they were not aligned at these large boundaries. So, okay, so then what we did, we went to our second transformation and we offset. We didn't align each large data structure at the beginning of a large page, but we offset them to avoid conflicts. And so this then actually finally did what we intended. We had the intended effect. Our page faults are down, but we actually here, the colors, I'm sorry, they're very hard to see the difference. One is brown and one is red. So that was not a very good choice. But we can see here are the TLB misses. This is our initial large page implementation, and here after we avoided the conflicts. The ERAT that had the high band is the initial implementation, the high band is gone. Same for the L1 caches. This high band that we had initially introduced is gone down here. And so now we had actually the desired effect. And this what taught us actually a very nice lesson now for our ultimate goal to automate this process of selecting the page size. Is that we have to really develop a performance model of what do we expect this transformation, what is the expected effect of this transformation. So we'd like to lower page faults, obviously. We'd like to lower TLB, but we also should keep, we don't want to introduce conflicts. So L1 cache miss rates, other performance miss data should remain constant. That is sort of what we manually went through here, and we saw this surprising effect. So we'd like to build these models of the effect that we'd like to see from a page size change, and then run the application and validate it. And once we have an appropriate model, the validation will be fairly straightforward. And then in understanding, did we have the desired effect, or do we have to retune? Are we not done yet? So here's just a summary of the effects. And just sort of seeing that, things across layers, if you look only at one layer, things might look fine, but you really have to look at effects throughout. And it's sort of a simple but nice example to show this effect. That, in our initial transformation, we had the desired page faults reduction, but we had huge rises in L1 caches and ERAT misses due to conflicts, and we eventually eliminate them. So we are currently working on automating this. And in terms of understanding what is, where do we have the most profitable pages, where are the most miss events taking place, and modeling the effect that we'd like to see, and then implement what we've done here so far manually in an automated fashion. Okay, and my conclusion, just to repeat, so this is work obviously going on in progress. We have the PEM infrastructure currently in place, and it's being used as a standalone tool. But it's certainly designed to be efficient, to be highly efficient, so we can use it online for this automation of this tool. Okay. Questions?
Do you have any questions?
Yeah.
Two questions. One is, when you talk about the overall overhead this introduces in sort of a production running system.
Yeah.
And then the second is, I forgot about the second question.
Okay, so yeah. So we have, in order to make this monitoring highly efficient, there's really a key that we're leveraging K42 implementation here, where each layer writes directly into it. So we have one global shared buffer, where each layer directly writes event into a buffer. So there's a lot of, if you're leveraging some existing tracing infrastructure that comes from one layer, you would require an OS call for every event that you're issuing onto the event bus, and that is too expensive. That we cannot tolerate high volume events. So here, every layer that issues events into the PEM library directly writes, it's basically a macro, directly write into the shared buffer. So we have one shared buffer per processor, actually, to write it, to make this very efficient. And certainly, the overhead depends on how much you're putting into the into the buffer and at what granularity. But at this granularity, we sampled hardware counters at 10 millisecond granularity. We issued performance events from the OS. Actually, very, very many. I mean, we had not only page faults, we had context switches, various RPC calls. We had many events from the operating system that we issued there, and it was almost not noticeable, within a few percent performance degradation. So it was very low at this point. But it's really a key that each time you issue an event, it's basically just a write. You cannot go through an expensive call chain there. So the OS, the event is not coming from there.
Have you had the
sorry, Hans had.
I'm sorry.
This is something I didn't understand. For the application you were looking at,
Yeah.
what were the page, I don't have any intuition of where the page faults are coming from. These were initializing faults? Or?
Yeah, so there were, actually there was throughout, if you look at, so here, they have actually, if you look at the overall run, go one back, you see that there's sort of, they are spread out, because you keep allocating new data structures. But now if you zoom in here, you see that the page faults arise at the beginning of each loop iteration. So it is initialization. You're allocating the new data structure, and then there is sort of one pass through the data structure, and then you have those pages in memory. And the rest of the iteration, you operate, you're basically, okay, page faults are really, they're still there though, but they're very low.
Oh, okay. But my intuition would have been is that if you're initializing, the main cost in the operating system would be actually writing the zeros to the page. And if you're getting fewer page faults on larger pages, I don't understand why that buys you much. Because you still have to initialize the same amount of memory. You're now doing it in a smaller number of faults, but each fault is much more expensive.
Wasn't one factor the TLB faults? I mean, the larger page sizes will certainly help reduce.
Oh, yeah.
Right,
Yeah. No, you still have, you see they also haven't gone down to zero. They're still there, so there are replacements. You recurrently reallocate the same pages. So there are also replacements taking place. It's not just a matter of the initial load. Then you would have like one little spurt here, and that you would be done with it.
Okay, but I don't understand the application. If you're deallocating and reallocating the same memory, then I don't understand why you're zeroing it at all and why you're getting page faults at all.
You're apparently calling CLX.
It's called a malloc, yeah. It's calling, yeah.
Because I was calling CLX.
Yeah, that's,
Right.
yeah, actually.
Well, no, but I don't know, because the cost seems to be associated with page faults. I assume the zeroing is going on in the kernel because you're allocating it from the kernel, but I just don't understand the behavior here.
But you certainly also, you're traversing it after you've allocated it.
Is the working set larger than the
Writing
physical
to it.
memory? A bit of order here, I'll put you on the queue,
Okay,
but
sorry.
Doug had his hand up earlier.
So this is maybe a suggestion for a topic in case people are interested. One of the commonalities across this and other performance tools and the like is the need for VM support for very fast, efficient logging.
Yeah.
And GCs already have this, so this is not like really hard to do, but there's usually no attempt to expose an API for middleware or monitoring or management.
Tiger has its monitoring management API, and it basically does what you described. It's a piece of shared memory you write into, and you can attach to the process and extract it. So, that was my question, whether she was
Hold
looking
that
at
thought.
that,
I asked
that's
my
all.
question in a minute, and Ben was queued, so.
So I'll just respond to that. That's a classic case where there's obviously overlap between the OS and the MRE or VE or whatever. I mean, you have to. I think somebody